Hello! In this video, we present the retrosynthesis of pentadeuterated tiagabine, an isotopologue that can prove useful in the investigation of the pharmacology and metabolism of this drug, and also serve as a reference standard for bioanalytical methods. This labeled drug can be visualized as a derivative of a deuterated 1-butene chain, which is attached at its carbon 1 to 2 identical thiophene heterocycles and at its carbon 4 to a substituted piperidine. Therefore, a strategy for its retrosynthesis involves successively disconnecting the rings that are attached to the deuterated chain and then subsequently identifying the necessary precursors for the deuterated chain, as we will see later. Initially, through a functional group transformation, the carboxyl group is protected to prevent its undesirable involvement or interference during the synthesis, as the ethyl ester 2, where the piperidine ring structure is bonded to a primary carbon atom that forms part of the deuterated chain, which suggests a substitution reaction, ultimately leading to a carbon-nitrogen disconnection to generate the deuterated bromobutanol compound 3 and the ester 4. The double bond of 3 functions as a retrone, and it can be generated through the elimination of a hydroxyl group in compound 5, which is subsequently obtained by means of a functional group transformation. The tertiary alcohol in 5 is bonded to a carbon atom that is substituted by 2 identical thiophene rings. This structural characteristic suggests for its formation a double addition of a nucleophilic thiophene reagent, such as a Grignard reagent, to an ester functional group. Operating under the premise of this particular idea, carbon-carbon disconnections produce the deuterated bromoester 6 and the Grignard reagent 7. The bromine atom, which is attached to the terminal carbon of the ester 6, could be prepared using a substitution reaction involving the primary alcohol of compound 8. The 1,5 relationship between the hydroxyl and the carbonyl in 8 suggests a carbon-oxygen connection, which then gives rise to the deuterated gamma-lactone 9 and ethanol as a raw material. A carbon-oxygen disconnection in 9 generates the deuterated hydroxy acid 11. The primary alcohol in 11 can be derived from the reduction with a deuterated reagent of a carboxyl group, which was generated through a functional group transformation to yield tetradeuterated succinic acid 12. The 4 deuterium atoms in 12 can be incorporated by deuteration of a triple bond, so the carbon-deuterium disconnections lead to alkyne 13, and molecular deuterium as the raw material and the source of the isotope. The functional group transformation of the carboxyl groups present in compound 13 results in diol 15. The 2 alcohol groups in compound 15 function as retrons, and based on an hydrocarbonylation reaction, 2 carbon-carbon successive disconnections. First generate propargyl alcohol 16 and carbon monoxide as a raw material. The second disconnection gives rise to the formation of acetylene 18 and carbon monoxide, both as raw materials. Grignard reagent 7 can be obtained from brominated thiophene 19, which, in turn, through a bromination reaction, ultimately generates 3-methylthiophene as a raw material. Finally, ester 4 can be obtained through the reduction of ethyl nicotinate 21 as a raw material. In summary, here are the main disconnection. In the next video, the resulting synthesis will be presented.